Welcome back. Thanks for coming back. Nice to see you all. So I'll continue the story today, and just to remind you what stage we were at. So last time we took an extremely classical viewpoint on CM theory, and we sort of centered everything around what one might call the holy trinity of CM invariance. So we talked about elliptic units, we talked about singular moduli, and we talked a little bit about Heegner points as well. And so I tried to emphasize as much as possible the explicit aspects of this theory, and I hope that message came across a little bit. This is really a topic that lends itself excellently to just explicit experimentation, and in fact many of the discoveries in this area, notably Gross and Zagier, were also discovered based on extensive numerical experimentation. So I encourage you to engage with that tradition and to also, as you're learning this topic, do lots of examples. I think maybe there's going to be an announcement about this, but there are also some discussion sessions, maybe Tuesday and Thursday, is that right?
Yeah, before the next quarterly meeting.
Okay, so there will be an announcement about that, and that could be an excellent, sorry to spoil the surprise for you.
That's okay.
But that could be an excellent occasion to engage a little bit with this. I'll be there as well as other people, so it can be great fun to talk about this. Okay, so the plan for today is to continue this thread, and we sort of set it up a little bit already I read you part of Gross's letter last time, and so today I want to dive in a little bit into some of the ideas that go into the work of Gross and Zagier, and I'll focus sort of on a setup that strips away some of the technical complications that you might encounter as you study the senior papers of Gross and Zagier, to focus in on some of the ideas that I think will help you have a better time when you read the actual papers. After that, I will also give some preliminaries for a purported theory of RM singular moduli, which is a p-adic theory. And so notably, I'll talk about rational co-cycles today. Okay, so the stage we were at yesterday is I gave you the following table, which you might remember, which was also a table that was mentioned in Gross's letter. The library was closed, so they had to compute it by hand. And presumably they computed much further to check Gross's guess about certain integers appearing in this formula being related to the exponents in the factorizations that you see in the J function, so the singular moduli and singular moduli minus 1728. And so today I'd just like to explore some of the ideas that go into what we now call the algebraic proof of the Gross-Zagier formula, or the algebraic part of the calculations, by focusing on just one of the entries in this table, or maybe more precisely two of the entries in this table, namely the high divisibility by 2 that we see in the first column at minus 11 and minus 19. Yeah, so we already noted yesterday, we wrote down Berwick's conjectures, or some of them at least, and this is one of them, and I would like to talk a little bit about the proof today. So that's where we'll start. Okay, so we'll talk about the following result, which was, at least the first part, conjectured by Berwick. And I'd like to complement it with, I think, a very nice sort of counterpart that was found by Stremler in a master thesis from 2024. Of course, all the key ideas are due to Gross and Zagier, but I think it's a nice find, so I'd like to completed with also a complement by Martin Stremler. And it's precisely Berwick's conjecture from yesterday. So suppose that we have a negative discriminant delta, for instance on this list, and suppose that it's 5 mod 8. Yeah, so like minus 11, minus 19 have this property. Then the following two properties are true. So the first one is that 2 to the 15 divides j of tau delta, where tau delta is any CM point of that discriminant. Okay, and I really mean, as we noted yesterday, it divides the singular modulus, not just the norm. Yeah? So meaning every prime above 2, if you raise it to the 15th power, in the field of definition of the singular modulus, we'll divide it. Okay. And actually, so the complement, that's the part of Stremler that I wanted to ask, or add rather, is that this exponent of 15 is optimal. Not always. It's optimal, in fact, if and only if the discriminant minus delta is represented by the following quadratic form: q x y z. It's a three-variable Turner. Oops, sorry. It's a quadratic form. 2x squared plus 4y squared plus 9z squared plus 4yz. Which is a statement that I hadn't really seen before his thesis. And there's an interesting remark to make about this. Yeah, so optimal meaning there's no larger rational number that you can put in the exponent for which this is true. Okay. Now, you might wonder, what are the discriminants that are represented by this ternary quadratic form? And in fact, there's very many. Yeah? So all of the discriminants of this form, so 5 mod 8, have a tendency to be represented by this. And in fact, the only known values that are not represented are the following 4 values. So 3, 43, 163, and 907. So those are the only 4 examples, if you look into the thousands, that you will find. Yeah? And so, in fact, so I might notice that in this criterion, that means that there should be a better divisibility. And in fact, 2 to the 18 is the optimal divisibility for the last 3. For the first one, you just get 0, so 2 to the infinity is the optimal one. So you might wonder if you could prove this. And in fact, yesterday at lunch, I was asked to maybe think of some nice projects to think about. And so let me give you the good news, is that in the discussion session, whenever it's going to be, Thursday or Friday? Today? Ah. Well, that makes me feel very sorry for Pacetti and Tornaria, because they will prove that these are in fact the only values that are not represented. They will prove it assuming GRH it is recorded, that's true. So I didn't think about that, but it's a joke, just for the people who are watching the recording. So these are the only ones. So because, I mean, there is a strategy for approaching this kind of problem. And in fact, it was carried out on a different ternary quadratic form, which was x squared plus y squared plus 10z squared, which was studied by Ramanujan. And he noticed that there's sort of a small list of counterexamples, or at least he knew most of them. And then with computer searches, maybe they found one more. And then it was proved, assuming GRH, by Ono and Soundararajan. And there's also other examples in Rouse's paper from 2014. And the key is, of course, that if you have a ternary quadratic form, you can associate a modular form of weight 3/2 to it. And this modular form of weight 3/2, it's a very structured thing. And so I think a strategy sort of presents itself in the sense that you can try and prove that this theta series has non-vanishing coefficients at all of these deltas that are 5 mod 8. Because you can maybe decompose it as, you know, some multiple of an Eisenstein series of weight 3/2, which has class numbers as its coefficients, and then some cuspidal part, which the coefficients of which are supposed to be very small. So if you can bound the size of the class groups well enough, then maybe you can show that the Eisenstein series will grow beyond control and can never be cancelled out by this cuspidal part. Anyway, so I haven't thought about it carefully, but it's something to think about, and it could be a fun thing. So I say we'll prove, but maybe we will discuss during the discussion session whether this can be made into a rigorous proof. In fact, I think the situation here is a little bit better even, right? Because this discriminant is quite nice. It's luckier than the one of Ramanujan. So it's 64, and then I think maybe if you take Shimura-Shintani in this higher level, whatever that might mean, you're faced with really elliptic curves of that conductor, and x0 of 64 is the Fermat quartic, so it splits up as 3 elliptic curves, and they all have CM. So that might make your life a little bit easier in making these kind of analytic estimates. So the CMness is very special to this setup. Anyway, that's just a comment. So I'd like to focus on these two statements, and I would like to give you some of the key ideas in the proof. Hopefully enough to give you the idea that you can sort of engage with these ideas, and I think if you understand the method of the proof of this small property, you will have a much easier time reading Gross and Zagier's paper. So that's a little bit my intention. Okay, so we saw, and maybe you feel it coming now already, last time I read this letter of Gross where the connection to quaternion algebras was suggested over dinner conversation by Kudla. And Gross said, well, I didn't really know at the time what the quaternion algebra was, but I did remember that the endomorphism ring of an elliptic curve in finite characteristic that's super singular is a maximal order in a quaternion algebra. And that turned out to be the right idea. That's sort of what he said in the letter. So that's what I want to explore a little bit further now. So how do we attack this kind of question? Well, we'll use the J function now. We'll use its moduli interpretation. And so we'll make two definitions. So first I'll let the elliptic curve E1 be given by this equation. Y squared plus y equals x cubed. And I'll consider this to be an elliptic curve over a ring called W, which is the ring of vectors of F2 bar, otherwise known as Z2 unramified, so the ring of integers in the maximal unramified extension of Q2. So this elliptic curve, of course, I picked because it has Cm by an order which I'll call O1. Oh no. Thank you, Fabrizio. He did that on purpose to embarrass me. But thank you. I much appreciate it. So O1 is going to be my name for the ring Z zeta 6, so maximal order in Q joint square root of -3. And all of these endomorphisms are also defined over W. And then finally, and this is really the reason for introducing this. So well, first of all, the discriminant is 3 cubed, but most importantly, the J invariant is equal to 0. Yeah? And so in the spirit of what we sort of hinted at yesterday, these tables, as was realized during the work of Gross and Zagier, the two columns should be viewed as two instances of differences of singular moduli, where a single singular modulus can be considered to be a difference as well of itself and 0, the J invariant of this elliptic curve. Yeah? So that's the reason for introducing this particular elliptic curve. So E2, I will not be able to write down explicitly. This will be some elliptic curve over W. With Cm by, well, the order O2, which will now be my order associated to this discriminant delta from the statement of the theorem, which is precisely of this form, because delta is 5 mod 8. The fact that I can always take an E2 that is defined over W, and also its ring of integers, its Cm action is defined over W, is true, but requires a bit of justification. Okay, so I can work over this ring W throughout. And now, what's the plan? So I'll tell you sort of some of the key ingredients without really proving them, but I just want to give you a flavor of what goes into the proof. And so there's two key equalities. We can roughly identify a couple of crucial points of action. So key equalities in Gross and Zagier. The first is that if I take the valuation in this DVR W, so with its canonical uniformizer given by 2, let's say, of the difference of the two J invariants. Yeah? Of course, I know that J of E1 is 0, but let me write J of E1 because, of course, this equality is true in a much more general setup than the example I'm doing here. This is given by the following infinite sum over all integers n greater than or equal to 1 of the size of the set of isomorphisms over the ring W modulo 2 to the n of these curves. So meaning I reduce these curves modulo 2 to the n, I check how many isomorphisms are between them, and I put that together into this sum. So this sum will always be finite. Now, this key equality, I mean, there's two ways to approach it. So nowadays we like to think of the J line as the moduli stack for elliptic curves. And then that makes it maybe unsurprising that you have such an equality. But you can also, you don't need this notion. Gross and Zagier, in fact, in their paper, check it explicitly on Weierstrass equations, essentially. So they write down general Weierstrass equations, E1, E2, and they check this by really checking how many isomorphisms there are modulo all the different powers of the uniformizer. They verify this equality directly. So you can pick whichever approach you like the most. Oh, sorry. This is the valuation. Let me add that, actually, in the ring W, which is a DVR. And so I'll take, in this case, we have uniformizer 2, so it's the number of times that 2 divides it. So this is the valuation in W. No, no. And that's why I wrote J of E1, which we know is equal to 0. But this is a general equality.
Or any pair.
Any pair of same elliptic curves, yeah. Okay, so, it's not clear that it's easier to count the right-hand side than the left-hand side. So Gross and Zagier, they carry on, they continue, and they show that there's another way to view this sum. And so I can continue to write n greater than or equal to 1. And now comes the part that connects it with quaternion algebras. I can count the size of these isomorphism groups by instead counting embeddings of the ring O2, which I've defined there on the left board, into the endomorphism ring of W modulo 2 to the n, which we'll very soon give a name to, of E1. Now, I'm not finished yet. There's buts and ifs to introduce, but I would like to already say how you might connect this to this. And that might be kind of clear. If I have such an isomorphism, what color should I pick? Let's do an orange. Then what I can do is I can produce such an embedding by considering the reduction modulo 2 to the n of the endomorphism rings, which is known to be an injection. So I can take the reduction of end W of E for either of these elliptic curves into end W over 2 to the n of E. And of course, end W of E, if I apply this to E2, I get an embedding of O2 into the endomorphism ring of W modulo 2 to the n of E2. And if I have an isomorphism, I can just make that equal through that isomorphism to the endomorphism ring of E1. So that's how I get an element in this set. So it's quite easy to see how to produce such an embedding from the above. What's much harder is the converse. Yeah? If I have only such an embedding, how do I produce anything to do with elliptic curves? I just have an embedding of this O2. And that's the theory of, Gross's theory of quasi-canonical liftings makes this precise. So I'll give a slightly less precise statement than what I could do, but just in the interest of brevity and hopefully some clarity, I will do it the following way. So there's a factor here. You have to be careful about how many times you counted things. I hope I was careful enough. But the thing is, if I consider all the embeddings, I don't necessarily know that they will come from this fixed E2, of which there could be many of a fixed discriminant. So to make this equality correct, I have to take the left-hand side, but I'll be a little bit lazy and I'll just sum over all the E2, and then I'll tell you how to remove this sum. So the sum will be over all the choices of E2 that I could have made, which up to isomorphism, there's really class number many choices globally of such an E2. And so for each of these choices, you will get an E2 defined over W, and you can put this sum together, and that whole sum of all these valuations will be equal to this. So let me say, I don't know if I... Slightly lazily, that different E2 in this sum, so this sum decomposes over the different E2. Likewise, this sum decomposes for all the embeddings of O2 into the maximal order up to conjugation. So the conjugacy classes on the right will correspond to the different elliptic curves E2 on the left. So that's a slightly finer statement than the one I've written down. So correspond to different conjugacy classes of O2 into end F2 bar of E1. Yeah. So there's finitely many such embeddings. Yeah, this is the one where I just put F2 bar, so where I reduce modulo 2. There's finitely many because this is inside of a definite quaternion algebra. And they break up to conjugation by units in this maximal order into finitely many conjugacy classes, and those correspond precisely to all of the choices of the E2 that you can make on the left. So let me say it in this way, and that should suffice for today's purposes. Okay. So those statements are all very general. Yeah. Oh, I'm sorry. Apologies. Yeah, thank you. I'll use the buttons. Yes? Oh, sorry, yes, I didn't say that. Yeah, W2 and W1, for that matter, will be the size of the unit group in O2 or O1, respectively. Yes. Yeah, sorry, I put the factor there to at least try to make the statement correct, but I hope I did that right. At least it fits with the calculations I'm about to do. So, okay, so explicitly, because of course this is all still very general, we now want to hone in on the specific situation of this theorem here on the left board. We can represent all of these quite explicitly. So, first of all, if I take end F2 bar of E1, that's the bit that Gross knew about quaternion algebras, at least so he said in his letter at the start of this project. This is isomorphic to a maximal order in a quaternion algebra. In fact, a very specific one. So here there's a unique maximal order up to conjugation. And it's the following one, where I, j, and k satisfy the usual multiplication rules for the Hamilton quaternions. So let me call this ring R1, and it's inside of B2 infinity, which is the Hamilton quaternions. And it's a maximal order inside of there. Okay, yeah, now of course, I mean, which one is I, J, and K? I still have a lot of freedom in choosing this isomorphism. And I'll give myself the liberty to choose it in such a way that I can also say what the reduction map is from the endomorphism ring of E1, which I know is just Z zeta 6. And I know that if I take reduction modulo 2, the endomorphisms will embed into the endomorphisms over F2 bar. And that embedding, I'm going to assume without loss of generality, is specified by sending zeta 6 to 1 plus I plus J plus K over 2, which is the sixth root of unity. Okay, so I will assume without loss of generality that this is precisely the reduction map. Okay. All right. So at least I know in the first term of this sum, when n is equal to 1, I know a little bit what the objects involved look like. So on the E1 side, everything is now clear, and now we have to figure out how O2 fits inside of there. But we also have to figure it out modulo higher powers of 2. And so Gross showed a beautiful result. So let me give names to this. So R1 was already my name for this maximal order, so endomorphisms mod 2. Let me call Rn the endomorphisms mod 2 to the n of E1. We can also be quite explicit about this. Now this is quite a difficult result to prove. But it showed that it's of a very predictable form. Namely, it's always equal to the image of O1, which I know I get in the reduction mod any power of 2, plus 2 to the n minus 1 times the maximal order. So it's a very explicit shape somehow. If I just know how this embedding of O1 is anchored inside of the maximal order, I know the endomorphism rings of over all of the powers of 2. That's what Gross shows. So explicitly, in our case, in our situation, this will be spanned by 1, and then I will have 2 to the n minus 1 I, 2 to the n minus 1 j, but then I don't touch the last generator. So that's 1 plus I plus j plus k over 2. In this specific situation. Again, the first statement is true in general. Okay, so we have a couple of black boxes, some of which are quite difficult to prove. I can see that. But now we're going to apply these and see how they come together. Because we're now in a great position to just start counting what's happening on the right-hand side of this equality at the bottom right. So let's do that. All right, so we're now in a situation where we can really explore also the kinds of arguments that Gross and Zagier make. In this specific example, Now, the case of the maximal order, that's a classical one. So there's work of Max Deuring, which already counts how many such embeddings there are up to conjugation, which we can just use. It's a perfectly general thing. And then all we have to figure out is, of these embeddings, what survives in these smaller orders of endomorphisms, mod powers of 2. So for n is equal to 1, Max Deuring shows a long time ago that if I take the set of embeddings of O2 into this maximal order R1, and I take it modulo conjugation by the units in this maximal order, then I get twice the class number many elements. And so I already told you, so we can split this result up also, because mod R1, those are the conjugacy classes of these embeddings. So they correspond precisely to the valuations, or the contribution to the valuation on the left-hand side, elliptic curve by elliptic curve, so E2 per E2. So in particular, if we sum over all the E2s, like in the formula there, we find that the contribution of the first term in this infinite sum on the right, which is just this. We have to correct now, because here I did modulo R1 star. No? And you see, if I conjugate such an embedding, there's also W2. W2 is the unit group in O2, but it acts trivially on these embeddings. So you get the same embedding if you conjugate by unit in O2, but I've multiplied by W2. So I've compensated for this fact, and so I get that I get 1/4 of the size of the full unit group times twice the class number, which is 12 times the class number. Right, so this number 12 here is significant. That's the first contribution, which already gets us a long way up to the 15, but we're not quite at 15 yet. Okay. All right, so when n is equal to 2, we now have to figure out, of all of these embeddings, which ones actually lie inside of R2, the next step up. And R2, it's up there on the board, it's O1 plus twice R1. So we can say that for any of the embeddings described in the first part here, I can look at the element that I get by just mapping the generator. Yeah? So I can take phi of 1 plus the square root of delta over 2. And that's something which I can always write as ai plus bj plus ck over 2 for some integers a, b, and c. And this will be inside of R2 if and only if a, b, and c don't just have the same parity, that's true for everything in R1, but are actually the same mod 4. If a, b, and c are the same mod 4, then actually this thing lands in R2. Yeah? And that's if and only if. Now, one thing you can notice is that you can conjugate by I or j to flip the signs of two of these three. So by just conjugating by I or j, you can arrange for a unique conjugate. So this has a unique conjugate by some u. Let's be more specific. It's unique if I take u to be in this unit group of size 4. Well, sorry, I and j, I should say. With a is b is c mod 4, which is precisely the condition that describes that the image of phi is actually inside of R2. Yeah? So i.e., that UXU inverse lands inside of R2, the endomorphism ring mod 2 squared. Yeah, so in particular, we have that in this conjugacy class that I can take, in each conjugacy class, I have my orbit of my units, and inside of this orbit, I've now defined this subgroup for which there's its unique conjugate inside of R2. And of course, the other units, they will preserve the property of being in R2 because the other units are accounted for by the 6th degree root of unity 1 plus I plus j plus k. So they will preserve, they're in R2, so they will preserve R2, they will preserve this condition. So in particular, we have that we can also calculate the next term in this sum, so W2, so of O2 into R2. It's 1/4 of the previous one, because that group has size 4. Yeah? So we have that this is equal to 3H delta. Now, already we're in a position where the first part of the statement now follows, because I have a contribution of 12 times for the valuation for each elliptic curve, and a contribution of 3 times the valuation for each elliptic curve. So that already adds up to 15. Yeah? So this shows that 2 to the 15 must already divide every such singular modulus, just by these kind of, well, not terribly deep type of calculations. So let's push it over the edge, and let's do also the sharpening that I promised by looking at n is equal to 3. And let me just say, so just to see where this ternary quadratic form comes in, you can do it in a very concrete way, namely the following. So suppose that minus delta is of the form q, x, y, z. So there exist some integers x, y, and z for that q that I had on the board earlier that gives me minus delta. Then the funny thing is I can just write down an embedding very explicitly, which is visibly not in R3. Yeah? And that's the conclusion of that proof. So if I define my embedding by defining on the generator the following expression. So I take my x, y, and z, and I make x plus 2z. I make x minus 2z. And then finally I put 2y plus z. And I divide by 2. You can now check by virtue of x, y, and z representing minus delta that this element really has the same trace and norm as this element in O2. So this defines for me an embedding. Yeah. So this defines an embedding. But its image is not in R3. Now, how do I see this? Well, I mean, so here, because x, y, and z are integers and they represent delta, you can check quite easily that they have to be odd. Yeah, so x and z here, yeah, so they have to be odd numbers. This z here in particular has to be odd. And that makes that these two guys are congruent mod 4, but not mod 8. Yeah, so that's why it's in R2, but not in R3. So I found here a single embedding of these guys in R2 that is not inside of R3. And that's in fact enough to conclude that this is true for any of the embeddings that I take. Because if it was wrong for another embedding, then I could only conjugate by the units I have left. And the units I have left are these 6th roots of unity, which are in R3. So they can only preserve the condition of being in R3. So that already shows that in that sum here, I can stop at 2. There's no contribution at 3 if I'm represented by this quadratic form. The statement was if and only if, but I'll leave the converse to you. So the converse, it's in Stremler's thesis as well. I'll leave as an exercise. It's essentially a similar argument. You can do it in a very elementary way. And another reason for leaving it as a converse is that once we have the theorem of Pachetti-Tornaria, we don't need to do this exercise anymore because we can just check the 4 values that remain. Okay. Yeah.
You're confusing the two-adic valuation of J of E1 minus J of E2.
Yes.
And norm of that.
So
because you sum over all the constants.
that's true. And so what I've written here, I've used frequently this weasel sentence here at the bottom, where I actually know how they split up over the different elliptic curves E2. It's the same splitting that I get by splitting up the embeddings over their conjugation classes by elements in R1 star. So this I've used several times now in practice. It's a bit sneaky, I agree. But that allows me to refine the result. It's just I don't know how to express in a neat way which conjugacy class I get. So I do it conjugacy class by conjugacy class, and so you see that in the argument, it's always about a given conjugacy class. Yeah. Ooh. But you're absolutely right to bring up that point. That's the sneaky part in my proof. Okay. And then this one, okay. All right. So I hope that gives you some idea. I spent a bit longer than I intended to on this proof. But hopefully it's useful to find an inroad into these proofs of Gross and Zagier, which are more complex, and so they will achieve, with similar ideas, you can prove the formula I had on the board last time for the valuation of the norm, or really for the full norm of the difference of singular moduli. But I think this gives you a nice inroad by isolating a couple of the ideas. And if you digest these, you'll have a better time with Gross and Zagier. Okay, now Gross and Zagier also give a second proof, and that's the one that I will put to the forefront in what is to come. They also give a completely independent analytic proof in their first paper together. So, and by proof, I mean proof of the formula, the factorization formula I had on the board last time. Now, it's a sophisticated argument, so I will sketch it in broad strokes. I will give you the overall strategy and the main steps, because those will be the ones that will come back when I discuss the p-adic context. And so I'll give you the key references here. So is the first paper of Gross and Zagier called On Singular Moduli. This paper is quite terse, so sometimes there's some technical points that are a little bit difficult to appreciate in the paper if you really want to get your hands on it. So I can also recommend a more contemporary source where a refinement is given of this result, but also some of these technical points, in my opinion, are more elucidated in this paper. And so it's called Singular Moduli Refined. So I recommend looking at these sources, potentially side by side. Okay, so the setup is the following. So many of you will be familiar with this. So given two negative discriminants, let's say that they're fundamental and coprime, then I get associated imaginary quadratic fields, which I'll call K1 and K2. Yeah? So the discriminant will be delta 1 and delta 2, respectively, and they span a biquadratic field, which I'll call L, which contains also a third intermediate quadratic extension of Q, which I'll call F, and F is real quadratic. So F is Q adjoined the square root of delta 1, delta 2. Now, what Gross and Zagier do is they consider a certain real analytic family of Hilbert-Eisenstein series. And I'll write down the formula, not because we will really use it, but just because I want to give you the idea that it's long and a bit complicated, but it's completely explicit. So that's the broader point I want to make. So it's a sum, yeah. So it's really the Eisenstein series associated to the characters 1 and chi of this real quadratic field F, where chi is the genus character that cuts out this extension L over F. Yeah? Okay, and so explicitly, this series was considered by Hecke a long time ago. It's a sum over all the German A's, that's an A, in the narrow class group of F, where I take chi of A and then the norm of A to the power 1 plus 2s. And then I take this inner sum, which is the usual lattice sum that you would write down.
The font is getting smaller.
Ah, yes, indeed. Can I get away with it this time? It's entirely correct what you say. It's quite small, but only because I don't really want to use the formula. I just want to point out a couple of qualitative things about the formula. So apologies for the small writing. I'll try and up it a bit. So what I can do is I can sum, except 0, 0 I don't want to sum, pairs of elements of this ideal A, modulo the action of the unit group of F. And then what Heegner was doing is he was trying to construct a holomorphic Hilbert modulo form of parallel weight 1. And naively what you would do is you would write down this sum, and you would hope that this gives you a nice, so ignore this one, you would hope that this gives you a nice holomorphic modulo form. And alas, this doesn't, this is just outside the range of absolute convergence, so there's what people usually refer to as the Heegner trick, where you put in this regularization factor. Yeah. And now it's getting really illegible. But it doesn't matter, I think. So Z2 plus n to the 2s. Yeah, there we go. Okay, so you put in this kind of factor that is supposed to regularize it, and you want to take the limit, s is a real parameter, as s goes to 0. And in that case, this is a trick often employed by Heegner. You do produce a holomorphic modular form in the limit. And so you can show that this converges, so it's an explicit expression, whatever it is, but converges absolutely for s greater than 0. Yeah, so we get a real analytic function. It also transforms for any value of s as a modular form of weight 1, 1 for the group SL2OF. And at s is equal to 0, so when you let this parameter tend to 0, you do obtain a holomorphic modular form as a limit. Unfortunately, you obtain 0. It vanishes. So those are sort of just the qualitative things I would like to point out. So recall from this, the real analytic family is like a Hilbert modular form of weight 1, 1, except it's not holomorphic, it's real analytic. And in the limit as s goes to 0, it vanishes. And it's completely explicit. Remember that as well. Okay. Now, the key idea of the analytic proof that you find in Gross and Zagier is you take this mystery series and you compute the following operations for it. So you take this modular form and you restrict it to the diagonal, meaning you put the two variables z1 and z2, which belong to two independent upper half planes, to be the same. So the upper half planes cease to be independent, and I now get a one variable modular form, which still depends on this parameter s. Then I will take the first order derivative with respect to s and specialize that at s is equal to 0. At this point, I'm left with a strange object because of this derivation, but because of the vanishing at s is equal to 0, this object still inherits modularity. So this object is still a real analytic modular form of weight 1, 1, but it's still not holomorphic. So to make it holomorphic, we can now take a holomorphic projection. And so those are sort of the steps that arise in Gross and Zagier's proof. All right, now all of these operations are fairly complicated, but explicit. And that's what allows Gross and Zagier to compute that the series that you get out has a Fourier expansion that is, well, relevant to this problem. A priori, there's a constant term, but I'll tell you in a second why I don't have to write that down. So I get in the Fourier coefficients a contribution for every n greater than or equal to 1. There will be a q to the n here. And I get two separate contributions to these Fourier coefficients. So the first is the log of the norm of phi n, the modular polynomial that I defined yesterday, evaluated at j tau 1, j tau 2, where tau 1 and tau 2 are any CM points of discriminants delta 1 and delta 2. Since I take the norm, it doesn't matter which ones. So there is that first contribution, which is minus the log of the norm of this modular polynomial, plus some other term which I'll just say it's explicit. Yeah? And when I say explicit, you should think that it looks a lot like the logarithm of the explicit formula in the factorization formula I had on the board last time. Yeah? So that's sort of the key of the proof. Now, if I take the first Fourier coefficient, I'm dealing with the first modular polynomial, which is just the difference of the two singular moduli. And so out comes minus the log of the norm of these difference of singular moduli, the integer I'm interested in, plus this explicit other integer. And the key point is that by looking at these expressions, but looking now instead on the left-hand side, I have just told you that I've produced an object which is modular, and it's of weight 2 and full level SL2Z. So it's inside of the space of forms of weight 2 and level SL2Z. And of course, that's not a huge space. That is just the zero space. So meaning this whole computation, all of these quantities that we've computed, they're all zero. Which is great because now you can move things to either side, exponentiate, and get the factorization formula. So that's a little bit the idea of the analytic proof. And that's all I had really planned to say about it today. Okay, so we'll get back to this and we'll see this come back in the p-adic context tomorrow. No. Yeah. All right. Any questions about this Gross Zagier part? Because we're going to completely shift gears now. And I'm going to try and tell you a little bit about rational co-cycles in the time that remains, which seemingly has nothing to do with anything I've told you so far. But like I said, the plan for today was to give also some preliminaries for RM singular moduli, which is really the types of objects that I will mimic, especially these kinds of analytic arguments for tomorrow. So I want to tell you at least a little bit about their definition. Okay. All right. Okay, so I'll try and strip it from as many complications as possible. So in particular, nothing will be p-adic yet. And I'll just focus on the simple class of rational co-cycles. Okay. All right, so it's a bit of a strange story, so bear with me, unless you've heard it before, which is entirely possible, because this part of especially these rational co-cycles, I should say that's covered also in these PCMI notes that I mentioned yesterday, so you can read about them in more detail there, and I'll follow this exposition also. So I will consider C of Z to be the additive group of rational functions on P1s. Okay? Yeah, and so far, I mean, I'm ramping up to sort of singular moduli for real quadratic field. It's completely unclear what the connection ought to be, but hopefully this will be revealed next time. So today I will just tell you what the main actors are in this theory, and then the payoff will come next time. So hopefully you can stay motivated until then. So I'll make this into a module for, well, really for GL2C if I like. I can do that. Where the action It's just the usual. I will consider the weight 2 action. I want this thing to be a left module. So I'll consider the following action. So I'll do the determinant, AD minus BC. And then I have a minus CZ plus A squared. With the formula a little bit different than what you might be used to. It's just because I would like left actions throughout. Okay, so my C of Z is now a module for GL2C with this action. And the goal, so the key actor in defining singular moduli for real quadratic fields, is to consider so-called rational cocycles. Which are elements of the group of cocycles for SL2Z, this arithmetic subgroup acting on this module that I've just defined. And so concretely, you can think of these just as crossed homomorphisms, if you like, of SL2Z into CZ that satisfy the usual identity, namely if I take two matrices, gamma 1 and gamma 2, I multiply them and I pull them through this map phi, then I get almost a homomorphism. I get that this is phi of gamma 1 plus gamma 1 acting on phi of gamma 2 via the action that I just defined. Okay. All right, a bit of a bizarre object, so let's break it down by giving some toy examples. And here's a good one to work through, which is very simple, but it's worth thinking about. So the input for this rational cocycle that I'm about to define is a cusp. So C will be a projective pair R, S of rational numbers. So this will be in P1 of Q. Yeah. Then I would like to define for you such a map, which will turn out to be a crossed homomorphism. So it's a map from SL2Z to C of Z, which takes a matrix gamma and sends it to the expression, which I'll define in a second, L of B minus L of, minus L of gamma B, where this L is a very simple rational function. If I give it input a cusp, then all it is it's S divided by SZ minus R. That's my definition of L. Okay, so it's a simple difference of two rational functions, where the first one is, sorry, I wrote B, and then here I wrote C. So let me pick C. C was a cusp, right? So PC, yeah, that's good. Right, so the first is a choice of input, that's this cusp, and the second depends on the input gamma that I feed it. Yeah? Where I acted the usual left way on P1Q. Okay, now here's an exercise for you. Verify well, first of all, that this P of C is a cocycle. It's nastier than you think, but it is true. Second of all, the input C that I fed it, this auxiliary cusp, doesn't really change much. So this cocycle depends only on the input C up to a co-boundary. So meaning the cohomology class is independent of the choice of C. Now, I could send you on your merry way and let you prove these statements, but let me tell you that broadly speaking, there's maybe sort of three ways that you could approach this kind of verification. The first is just compute it, which is the worst way. 2, yes. But if it's new to you and you're serious about learning this theory, it's a good instructive exercise to do, if only to appreciate the benefits of the other methods. Okay, make it sound like it's a crazy calculus. It's not that bad, but it's worse than you think. All right. So use a direct calculation. Yeah, meaning you just check that it's a crossed homomorphism expressing that identity. Okay, the second, which may also explain a little bit where this kind of strange object comes from, is that there's an identity that most of you will know already, and if you know it, you can use it. If you take the weight 2 Eisenstein series, classical object, which is holomorphic modulo form of weight 2 for SL2Z, except it's not quite invariant under the action of SL2Z. So it's not quite a modular form. And its lack of invariance is measured by, well, if I act on it by 1 minus gamma inverse on the right, yeah, that's why the inverse is there, then actually I get up to some explicit factor, some 2 pi I or something, I get p infinity of gamma. Yeah, meaning infinity is my choice of base point there, 1:0. Now this identity, of course, immediately implies that this is a crossed homomorphism without any calculation. Of course, you have to calculate to get the identity, but if you already know it, you immediately get that. And it's as if we've trivialized this rational cocycle by passing to this bigger module. E2 is not a rational function, but if you allow yourself to get to this bigger class of analytic functions, then it behaves like a coboundary. So the proof is as hard as proving that a coboundary is a cocycle. The third option is to use modular symbols. And this will be useful also in the more complicated examples that we're about to do. So modular symbols here will be taken to mean maps that take pairs of cusps and spit out some element m. I can do it really for any module. Yeah? In particular for the module that we're considering today, which satisfy the following properties, so such that it has to be true, and so typically this is denoted with these curly brackets, A comma B, I don't know why, but it's a tradition. It's antisymmetric, it's additive, oh, sorry, I don't know what that means. Yes. And the action of gamma is good for it, meaning that if I act on the element of the module, again, it's the left module, then it's the same as acting on its inputs. So these three together constitute the properties that define a modular symbol. Now, if this is true, you can check quite easily using these axioms that for any cusp C, I can make a rational cocycle, or a cocycle valued in M, by defining the rule that associates to gamma the modular symbol of my base point C, this cusp C, comma, gamma acting on C. Yeah, so this is a 1 cocycle. Okay, so you can verify this quite easily from these defining properties. And then you can define a clever modular symbol that'll show for you without pain and suffering that this thing is indeed, I can still use this, a 1 cocycle. Okay. All right, so let me tell you about the object that we really care about, which is, this is more of a warm-up, but it's an instructive one to do. And that's the cocycles that were defined by Knop at the end of the 70s. Yeah. So I mean that its cohomology class is independent of C. So if I change C, I only change the cocycle up to a coboundary. Okay. All right, so the example we really care about is the following. And this example is due to Marvin Knopp, 1978. He was thinking really about Eichler-Shimura in negative weights. It's quite a different kind of motivation. But never mind. So what he did is he associated to a quadratic form with positive discriminant. Yeah, and when I say quadratic form, I mean primitive integral binary quadratic form. The discriminant does not need to be fundamental or anything. It can even be a square. Okay, so the first thing I'm going to define is a set, which I'll call XF, which is the extended upper half plane, so I'm including also P1 of Q, minus the set of all the geodesics, which I'll tell you about in a second, of Q, that are SL2Z equivalent to my fixed choice F. Yeah. Now, what does this mean? I can look in the upper half plane at any quadratic form F that is SL2Z equivalent to a fixed one that I choose, and it has two real roots, yeah, which sits somewhere on the boundary. It could be at infinity if the form F is split. If it's non-split, it'll be two conjugate real numbers. And in any case, I can connect the two roots of this quadratic form. So I'll have an RQ, if you will, and a second one, RQ prime, to get a geodesic in this way. And that's what I mean by geo of Q. Now, there's infinitely many quadratic forms in this SL2Z orbit, so there'll be infinitely many geodesics all over the place, but it's measure 0, and XF is the complement of this measure 0 set. Okay. Now, for any 2 points, for x and y, in this set XF, define the sign relative to Q of x comma y to be, well, the element that is either 0, 1, or minus 1 that gives me the intersection number of the geodesic between x and y. So x could be somewhere here, maybe y could be somewhere here, and then I get a geodesic in this way. My two geodesics, they come with a natural orientation as well. And I take the intersection number of these two geodesics in the upper half plane where I fix an orientation once and for all. Yeah? So whether you're right-handed or left-handed doesn't matter, you just fix it in the beginning and then you have a well-defined notion. Okay. I found another Hagoromo stump, so that's good. Okay, so to be the intersection between the geodesic of Q and the geodesic that goes from x to y as depicted here on the right. Okay. All right, so a bit of a strange definition maybe. And so you should think of, well, the sign is crucial. But you should think of this XF, it's not a big deal. It's just sort of, it expresses what it means for a point to be a random point. You don't want to make an awkward choice. So if you choose in XF, you're assured not to make any awkward choices for what I'm about to say. And this is what Knopp was doing. So, Knopp said, take a base point B that's generic. Then make the following definition. He didn't call it this, but I'm calling it. Knopp sub b comma f. Yeah? So my two choices are reflected here, the base point, which is not so important, and the quadratic form f, which is very important. And I define a function from SL2Z to C of Z. And that function is the following. So I take a matrix gamma in SL2Z, and I send it to the sum over all quadratic forms equivalent to f. So it's an infinite set of forms, SL2Z equivalent to my fixed given form f. And I do the following. So I take the sign relative to Q of the pair B comma gamma B. Yeah. And of course the set XF is gamma stable, so that makes sense, times L of the root of Q. Yeah? So where, let me just say that if Q is the form ABC, RQ is just this root with the plus sign. There's another one with the minus sign. Okay, so that's the function I define. Now, already, I mean, it's not obvious that this sum makes sense. I promised you I would go to the rational functions. Luckily, this sum is actually finite. Yeah, so that's one of the exercises in the notes. So the exercise is verify that this expression really is, it's defined, yeah? So meaning it's a finite sum. Verify that it's a cocycle. So it really is an example of a rational cocycle. And verify that its cohomology class, again like before, is independent of the choice of input point B in XF. Okay, now, of course, so the hard one is the second one, is to check that this is a cocycle, and I've given you in this toy example three options. So if you work through them, you will have a clear preference for which one you prefer. I have a preference too. Hopefully we have the same preference. If not, that's an interesting discussion, of course. Now, maybe one thing to mention, let's see.
So what's
Yeah.
an LRQ again? Is it
Yeah.
volume 2?
Yes, indeed. So I view RQ here as a projective point. I said it before in P1Q, but it doesn't really matter. So I view it as a projective point here where the first coordinate is minus b plus square root of delta, and the second is 2a. And now it makes sense also in cases that a is equal to 0. So I just pulled a fast one on you with this expression, but it's really the projective pair. So I want to also allow my quadratic forms to have square discriminant. That's actually the case I'll focus on next time. So it's a bit of a degenerate case, but nonetheless, I would like to allow that at this point. Okay, I could give you an example, but maybe in the interest of time, I'll leave that for the discussion session. It's nice to work out some explicit small examples of this, and I'll just make one comment, one remark to finish. I have 5 minutes, right?
Yeah.
Okay, good. All right, so if I look at my list, the first one, you can do the first one. The first one is also in the literature. The third one will be your preferred choice if you work through them. The second one is also interesting because it's not so clear if the second one can even be made to work here. But I just want to mention very nice work. So there's work. So what plays the role of E2 for this knob cocycle? That's a more complicated story. And I just would like to mention that there is work of Duke, Imamoglu, and Toth that studies a certain generating series for geodesic integrals of the J function, which I'll call curly GF. And as a function, it has a very explicit Q expansion, which is the following. It's a Q series whose nth Fourier coefficient is the integral from some auxiliary choice of Z0 in the upper half plane. It doesn't matter which choice you make. To gamma of f, a generator of the stabilizer of this form f, which is the input also of the Knop co-cycle. Sorry, let me make this a little bit bigger. So gamma f Z0. It's the endpoint. So it'll be some integration between 2 points in the upper half plane. And what am I going to integrate? I'm going to integrate J sub n of z, and then I put the form dz over f of z to make that integral nicely well defined, and then I collect these as q to the n. Now what is jnz? That's the only thing I haven't explained for you. When n is equal to 1, it's the j function that we've seen already, and when n is not necessarily equal to 1, it's the unique polynomial in j that has a Q expansion that starts with Q to the minus n and then has nothing until the Q term. Yeah? So meaning its principal part is really Q to the minus n, and it's in Cj. That defines it uniquely. So that's what this Jn is. So this work of Duque, Mogul, and Toth studies this sort of bizarre series. It's a holomorphic function on the upper half plane, but it's not quite invariant. And I can tell you that what they prove is sort of a counterpart of the second method of proof, if you will. They prove that if you take this GF and you hit it with 1 minus gamma inverse, then you get almost the Knop co-cycle. So you get the Knop co-cycle associated to f of gamma minus the Knop co-cycle associated to minus f of gamma, where if f is a, b, c, minus f is minus a minus b minus c. So you get sort of a difference of 2 Knop co-cycles. So it's pretty close to allowing you to prove something for the Knop co-cycle itself using the second method.
Did you get a way through action?
Yes. Yeah. Okay. All right. So that sort of concludes the Archimedean story. So hopefully that wasn't too bizarre at the end. So these 3 boards maybe contain some mysteries. But next time I will tell you why we made all these definitions by talking about joint work with Henri Darmon, where we take these co-cycles and we make a certain p-adic variance of them, whose evaluations, which I'll define also next time, experimentally showed a lot of similarities to all of these kind of factorization phenomena that we studied for differences of singular moduli. So next time I will define that for you, and then I will explain how maybe a purported p-adic Kudla program can help to prove some of the observations that we made. So next time will be p-adic, and I will tell you why this construction is useful, and we will move to the RM setting. Okay, so with that, I'll stop for today.